The family of alkenes is going to be our first family that has a functional group in it.
Be sure to do the in-text problems as you read, and notice we're not going to cover every single section. The alkenes is the functional group, or the functional group class, that has a carbon-carbon double bond in it. The smallest molecule with a carbon-carbon double bond is something called ethylene. And you may have heard of polyethylene and things like that. And it is ethylene that has been polymerized, which we can talk about later. Now, the carbon has 3 groups on it. So that means 3 things trying to get as far away from each other as possible goes into the trigonal planar shape, which gives you 120-degree angles. This means that carbon-carbon double bond and its attachments are planar. And it's very rigid. That double bond does not allow rotation around that carbon-carbon double bond. Around a carbon-carbon single bond, it's very floppy because you can have rotation occurring. But a carbon-carbon double bond is rigid and does not rotate. So we have this little bit of rigidity inside a molecule there. Because 2 hydrogens have been removed to make that double bond, the general formula for alkenes is CnH2n, just like for the alkanes. The other functional group that we're going to analyze in this chapter is something called alkynes. Alkynes have a carbon-carbon triple bond. A carbon-carbon triple bond is linear because you have 2 groups on each carbon. And it also gives a little bit of rigidity to the molecule, not that there's no rotation around it, but that it's linear, which is different from the kinkiness of the alkanes in general, or what you would find in the rest of the carbon chain. Alkynes, because 2 more hydrogens have to be removed to form the 3rd bond, have the general formula CN2H2n-2. So there are 4 hydrogens removed from the alkane formula in order to form a triple bond. These 2 functional groups, alkenes and alkynes, are referred to as unsaturation, which comes from that the carbons are not saturated with hydrogens, so that the having less than all the hydrogens gives them the double bonds or the triple bonds, so that's unsaturation. Their physical properties are very much like the alkanes. They're nonpolar, and any part of the molecule that has a carbon-carbon double bond or a carbon-carbon triple bond is hydrophobic. To name the alkenes and the alkynes, we're going to use a similar method as we do for the alkanes. You find the longest chain and count the number of carbons, but make sure that that longest chain has the functional group in it. You don't want that sticking out to the side. So you find the longest chain that has the carbon-carbon double bond in it or the carbon-carbon triple bond in it. Then the number of carbons gives you the prefix, and instead of adding "ane" on the end, you're going to add "ene" or "ine." If in the longest chain you have a carbon-carbon double bond, then you add the ending "ene." If in the longest chain you have a carbon-carbon triple bond, then you use the ending "ine." Now you always set the numbering system so that the functional group gets the lowest possible number. So count from either end of the chain, and whichever number gives that functional, the first carbon in the functional group, the lowest number, you pick that numbering system. Then you put that number in front of the name and then a dash after it, and then you find all the substituents, name and number them according to the original numbering system that you used for the functional group. You don't have one set of numbers for the functional group and another set for the substituents. It's all one numbering. Here is an example. You can see that the longest chain that has the double bond has 7 carbons in it. So that gives me hept as the prefix. -ene will be the ending because there is a carbon-carbon double bond. If I number from the right here, you can see that the first carbon in the carbon-carbon double bond is a 4. If I number, you would see that the first carbon in the carbon-carbon double bond is a 3. I choose that numbering system. So now you can see it's 3-heptene. The only thing left to do is to notice there is a substituent, the methyl group, and it's on the number 5 carbon. It's 5 because that numbering system is set by the functional group, and so I name it 5-methyl-3-heptene. Now what I'd like you to do is stop and do the same thing for these two structures. Name and number them, put substituents on. Remember, the longest chain with the double bond in it. To do this first one on the left, you can see that the longest chain has 6 carbons in it. That gives me hex as the prefix. There is an -ene in there, a carbon-carbon double bond, and I can number it from either end and get 3-hexene. So I know it's going to be 3. However, if I number it so that the top carbon is number 1, the methyl group gets a lower number, and so I call that 3-methyl-3-hexene. I would not call that 4-methyl-3-hexene. To name the one on the left, I'm going to recognize it's a cyclo compound, so it's cyclopent because there's 5 carbons in there. Then there is an -ene, so I make it cyclopentene. The number 1 carbon will be one of the carbons in the carbon-carbon double bond. It gets the lowest numbering. Now, numbering always goes through the double bond, so the methyl group is on the 3rd carbon because the first one is the top carbon, the second one is the bottom carbon in the double bond, and number 3 will be where the methyl group is. In this molecule, I'd like you to name it, number it, and put the substituents on. We see that this is a ring compound, so we're going to start with cyclo. There's 5 carbons in the ring, so it's cyclopent. There's a carbon-carbon, so it's cyclopentene. Then we have to name and number the substituents. Number 1 is one of the carbons in the double bond. Number 2 would be the second carbon in the double bond. So since the molecule is symmetrical, it doesn't matter which way I go. So I'm going to name and number where the substituents are. It's understood that the first and second carbon are in that double bond. So all I have to do is name and number the methyl groups. It's a dimethyl cyclopentene. And if I count around, you will see that it's 1, 2 through the double bond, 3 for a methyl group, 4, then 5 for a methyl group. So 3,5-dimethyl cyclopentene. Go ahead and draw the structure of 4-methyl, 3-ethyl, 2-hexene. To do this, the first thing I do is draw in my hex, 6 carbons. Then I'm going to place my double bond is going to be between the 2 and the 3 carbon because 2 starts the double bond. Now I put in my substituent. On the 3 carbon and the 4 carbon, I'm going to have an ethyl and a methyl. So on the number 3 carbon, there is an ethyl, and on the number 4 carbon, there is a methyl. Another way to do this molecule would be to draw out the carbons. Now you can see I'm putting the number 1 carbon on the left. Number 2 starts the double bond. Then I place the ethyl and the methyl on the number 3 carbon is the ethyl, and on the number 4 carbon is the methyl. We've learned about constitutional isomers, compounds that have the same formula yet have different connectivity. We're introduced now to another type of isomerization, and that is something called cis-trans isomerization. If you recall, I told you that a carbon-carbon double bond is planar and rigid. That means that if you have one group attached to a carbon on one side of the double bond, it stays there. There's no rotation around that double bond. So if you look at the compound on the left, you can see that the two groups are on the same side of the double bond as each other. The methyl and the ethyl are on the same side of the double bond. If you look at the compound on the right, you can see that they are opposite or across the double bond. As a result, the compound with the two groups on the same side is given the identification as being cis, and the one on the right, which has the groups across the double bond from each other, are given the term trans. So, if I'm going to completely name the compound on the left, I call it cis 2-pentene. Why 2-pentene? Because you can see there's 5 carbons in the longest chain, and the double bond starts at the second carbon. And it's cis on the left because the two groups are on the same side, and trans 2-pentene on the right because the two groups are across from each other. So now we've been introduced to two different types of isomers. We have the cis-trans isomers, which are also called stereoisomers. They differ in the 3D arrangement of the atoms. The connectivity is really the same because you can name them the same thing. Besides the cis and trans part, you name them the same thing. But with constitutional isomers, the connectivity is different, so the name is different. The only difference between cis-trans isomers in the name is the prefix of cis or trans, and then the three-dimensional arrangement of atoms that results because of that. If you look at the examples down here, you can see that cis-2-butene and trans-2-butene are cis-trans isomers or stereoisomers, and you can see that 1-butene and cis-2-butene are constitutional isomers. You see the rest of the name actually changes. Comparing names is a really good way to identify constitutional isomers. If two compounds have the same name other than cis and trans, then they are not constitutional isomers. They have to have different names. If all that differs between them is the cis and the trans, well then they're the cis-trans isomers that we sometimes call stereoisomers, and the three-dimensional arrangement is different. Now that we've been talking about unsaturation, and that the alkenes and alkynes are called unsaturated compounds, and you may have been saying that there was some connection in your head. You may have been saying, oh, there must be some connection between what you hear about unsaturated and saturated fatty acids, and you're right if you're trying to make that connection. Remembering that saturated means that the carbons have all the possible carbons that are on there, and there are no double bonds or triple bonds. Unsaturated means that some hydrogens have been removed, and so you have a double or triple bond. Well, this is what we see with the unsaturated and saturated fatty acids. A fatty acid is a long carbon chain that has a functional group of carboxylic acid at the end. Now, when we have a fatty acid that has no double bonds in the chain other than where the carboxylic acid is, we call it a saturated fatty acid because all the carbons have as many hydrogens as possible on them. When we have unsaturated fatty acids, then we have a carbon-carbon double bond somewhere in that chain, and sometimes there's more than one. If it's a single carbon double bond in the chain, we call it a monounsaturated fatty acid. And if there's more than one double bond, well, then we call it a polyunsaturated fatty acid. Fatty acids are in fats and oils. The composition of the fatty acid will determine whether or not the fat or the oil is a solid or a liquid at room temperature. Really, fats are compounds in this class that are solids at room temperatures, and oils have almost the same chemical composition as fats. They're just liquids at room temperature. That's the difference between a fat and oil, is their melting point. So how does the fatty acid composition determine whether or not the fat or oil is a solid or a liquid at room temperature? It has to do with the double bonds or the unsaturation. If I look at a fatty acid that has a double bond in it, you will find it's U-shaped due to the double bond being rigid, and they're usually cis. The cis fats, fatty acids, have that stiff double bond in them with the groups on the same side. It gives them a U-shape, and they tend to not stack very well with each other, so the melting point is high. The more double bonds that are in a fatty acid, the higher the melting point. When we look at fatty acids that have no double bonds in them, or saturated fatty acids, we find that their arrangement is long and stretched out. That long, stretched out, kind of like a rope, means they can stack well on each other. Stacking well gives them a high melting point. A high melting point means that they're going to be a solid at room temperature. This melting point characteristic determines their behavior in your arteries. If you have a fatty acid that is unsaturated, its U-shape doesn't stack well, and so in your arteries it's not going to stack well on the walls of the artery, and they tend not to deposit on the sides of the artery and cause hardening of the arteries. Whereas when you have a saturated fatty acid, they're long and ropey and stack well on each other, and they tend to deposit on the sides of the artery and cause hardening of the arteries. So when you hear about saturated fatty acids being good for you, it's because unsaturated fatty acids being good for you, it's because they do not deposit in your arteries. And saturated fatty acids or trans fatty acids are bad for you because they have this long, stretched out, three-dimensional shape that allows them to stack well, and so they tend to deposit on the sides of the artery. Here is a picture of a saturated and an unsaturated fatty acid. Stearic acid is saturated, and if you look through that structure, you're going to find there are no double bonds. Oleic acid, if you look at its structure, you're going to find a double bond approximately in the middle of it, and you can see that it is cis. That cis double bond causes the oleic acid to have a rather U-like shape. And you can see by looking at stearic acid, it would be relatively easy to stack them. And so we have a high melting point, and it's a solid at room temperature. Oleic acid, though, is not going to be easy to stack it, so its melting point is very low, and it's a liquid at room temperature.